Okay, the ratio test. Ratio test works especially well when you've got factorials. And if you've noticed, a lot of your formulas coming up later in the chapter are littered with factorials. Or if you have exponential powers, the ratio test is the way to go. Out of the 10 tests, this may be the most important of them all. I think it gets used the most. It's definitely top 3, but I think the ratio test gets used the most. So it's important. Here's what it says. If you can't really tell if something converges or diverges, and you use the ratio test, the word ratio means a fraction. A ratio is a comparison of two numbers. So what you want to do is you make a fraction. And you make it inside of absolute value bars. What you do is the numerator is the next term out. It's term n plus 1. And you stack it on top of term n, a sub n. And then you let this fraction ride as n heads out to infinity. Just let the n get really big. And you see what happens to it. If it comes out less than 1, it converges. In fact, it converges absolutely, but the absolutely part isn't really important in section 9.6. We're not doing absolute versus conditional here like we did before. All right, same thing. If this fraction is greater than 1, then it diverges. And I don't know why the book felt the need to write this second little part here. Oh, by the way, if it becomes infinity, it also diverges. I mean, last time I checked, infinity was greater than 1, so I'm not real sure why this is here. Maybe because infinity is a concept rather than a number, that they felt the need to put that just to be extra accurate. But the bottom line is, hey, if this thing's less than 1, it converges. If it's greater than 1, it diverges. If it's equal to 1, the ratio test fails. But not to worry, there are 9 other tests to choose. So that's the bottom line. Let's try some examples and see if it makes sense. Use the ratio test to determine the convergence or divergence of the series. Even if the directions had not said use the ratio test, I would have immediately thought of it because, again, the ratio test works especially well for problems with factorials and exponential powers. This happens to have both of those, so immediately I'm going limit as n approaches infinity. And the ratio test, again, ratio means fraction. What you do is you turn this into a fraction. You basically bump all the n's up to n plus 1s. So this will become n plus 1 factorial over 2 to the n plus 1 power. All right, divide it by the normal. Expression that you were given. We'll see what that comes out to. Now, because a lot of times this is fraction over a fraction, just to save myself time, I usually don't write that first step. You know how dividing by a fraction is the same as multiplying by the reciprocal, so what I'll do is I'll just take the numerator and I'll put it first, and then instead of dividing by this fraction, I'm going to write the second part over here upside down as a reciprocal. And usually, like I said, I won't even write that first step. I'll go immediately to there just to save some time and effort. Now, of course, canceling will occur. 2 to the n will cancel into 2 to the n plus 1. There's just one extra 2 in the denominator there, so that'll become a 1/2. And the factorials will cancel as well. N plus 1 factorial is n plus 1, but then the rest of it's going to cancel with the n factorial down below, so that'll just turn into an n plus 1. So we have n plus 1 over 2. Now remember that it's the limit as n approaches infinity. We're plugging an infinity in, so this actually will turn out to be infinity. Now we try the test. Infinity is greater than 1, therefore the series diverges. Normally I would encourage you on a test or quiz to say that it diverges by the ratio test, but the directions said use the ratio test, so I didn't bother there. All right, next up, number 2. All right, let's see if this converges or diverges. Ratio test, here we go. Okay, there's the basic setup. We'll take this original. I'll put the original down low on the bottom here in the denominator, just the way I see it. And then in the numerator, I crank all the n's up by 1 to n plus 1. So that'll be an n plus 1 in front. And it's going to be 2/5, not to the n plus 1 power, but to the n plus 2 power. N plus 1 plus 1, if you will. All right, now let's cancel some things out. The n plus 1 and the n will both cancel. Remember, you're heading towards infinity, so L'Hopital's rule assures you that that's 1 over 1. Plus, if you think about it, what's 1,000,001 divided by 1,000,000? That's pretty close to 1. The other part here in green, you have 2/5 to the n plus 2 over 2/5 to the n plus 1. It's going to be an extra 2/5 on top. So if you get 2/5 up in the numerator, nothing left down there. So that whole thing is going to come out to the absolute value of 2/5, which is just 2/5. And 2/5 is less than 1. And since 2/5 is less than 1, the series converges. And that's the ratio test. All right, let's try another. All right, if I saw this on a test or quiz, I might think about AST because there is an alternating component, a blinker light, if you will. But the rest of it, with all those exponents on there, I think it would be tough to try to compare it with a P-series or geometric. I just don't see how that we could swing that. So I'm going to use the ratio test. The ratio test will end up becoming my go-to, and hopefully yours as well. All right, as you can see, I set up the ratio test. The limit as n approaches infinity. I cranked all the n's up to n plus 1s. Instead of making a mega fraction, I just multiplied by the reciprocal. So the original is upside down. What's really cool is the blinker light will always cancel. Because -1 to the n plus 1 and -1 to the n are off by a power. So one of them will be a 1, one will be a -1. I don't know which is which. But there's absolute values around the whole thing, so you can just ignore those. You want to write them just so you show me that you realize they're there, but they're not going to take part. All right, let's cancel some more. I can see that the n plus 1 to the third and the n to the third, by L'Hopital's rule, are both just going to turn into 1s as n comes up to infinity. And that leaves us with the rest, which is 3/4 to the n plus 1 over 3/4 to the n. There's an extra 3/4 up here and nothing down here. So this entire thing will come out to 3/4. And since 3/4 is less than 1, the series converges. All right, I made up one more example, number 4. And this will finish up the ratio test for today. Directions I've changed a little bit. I just said verify that the ratio test is inconclusive here. Ratio test is not going to work too well. Let's try it and see what happens. So again, I took the original summand. I wrote it with n going up by a power, so I have 1 over n plus 1 cubed. Dividing by the original is the same as multiplying by the original's reciprocal. And via L'Hopital's rule, you can cancel the n to the third and the n plus 1 to the third are both going to become 1s. That makes this entire thing 1. But remember, since the limit is 1, the ratio test is inconclusive. I'll write that out formally. And as you can see down below, I said that the ratio test never works in a P-series. It's always going to come out to 1. Besides, why would you want to use ratio test on that? I can look at that original problem and in about, 2 seconds, tell you that it converges because P is 3. So there are certain places that the ratio test is very helpful. There are certain places where it's not helpful. And so that's why it's good to know all 10 tests. All right, that concludes day number 1. That's your ratio test. We'll do the root test next. And that'll wrap up the first half of Chapter 9.